Swayam Prabha. Digital India. Educated India.
So, who is called father of coordination chemistry? Huh? Warner. He is a Swiss guy, Switzerland. He is the one who started looking at some of this chemistry during 1990 or 20, something like that. By that time, already so many things he found out. Otherwise, chemistry of carbon compounds were well known. Ionic compounds, covalent compounds were all studied, but something on the coordination compounds is the first one to study, and it is, if you look at the way that people have understood, it was not so easy to understand the structure and bonding of these molecules. So, it was very easy to understand the ionic molecules and ionic compounds and covalent compounds, but not the coordination compounds. So, that is why it was called complex. So, he is the one using some of these metals and particularly ammonia, water, chloride as ligands, fluoride and other ligands. So, these are all commonly available, right? Water is there, and sodium chloride is very common, right? Ocean, Indian Ocean has plenty of sodium chloride, isn't it? So, that also is there in the earth crust. So, chloride is a common ligand. Ammonia also is there, okay. Urea, after we consume proteins, protein finally at the end they get decomposed into urea, and the body gets rid of urea, and the urea will give you finally ammonia, right. If you do not get rid of the urea from the body, then you are diabetic, highly diabetic, your body is not working. So, ammonia is also there. So, these are some of the molecules that are commonly available in nature, and these are some of the compounds that are already there in the nature. But people wanted to understand why only this many number of molecules that are present around the metal, right. So, like in carbon compounds, carbon always combines with other elements. Carbon, hydrogen is very common, right. Carbon, nitrogen and other combinations are all possible. But in this metal complexes, the metal ions are combined with only some limited numbers. So, those days there were no crystallography, there was no X-ray diffractometer to understand what is the structure of these molecules. X-ray diffractometer will give you structure of the molecule. If you have a molecule, if you go to give a crystal to guy who is operating X-ray diffractometer, he will collect data and he will tell you what is the structure of that. Like you stand in front of a mirror, you see your image, right. So, similarly directly you do not see in image from the X-ray, but indirectly you can obtain an image. That is what it is. So, like I said, if you stand in front of a mirror, you get your image, you know what you are. But the same way we cannot do with molecules. You cannot put them in front of a mirror and see what the structure, but instead X-ray diffractometer indirectly gives you that image, okay. So, those days there were no X-ray diffractometers to find out what is the structure of these molecules. So, through spectroscopy, through other studies, people came to know that certain metals like to combine with only this many number of groups. So, these are whatever that I have written here, simple, these are called ligands. Many varieties of these are all called monodentate ligands because they contain only pair of electron. Of course, oxygen has two pair of electrons, but often there is only one pair that participates in the bonding. Chlorine has many, but again often it participate only one pair. Sometimes two pair also can participate. Okay. So if you take similarly ethylene diamine, which is something very common. So on nitrogen you have a pair of electron. So there are two different nitrogens. So and these two are connected through ethylene bridge. So it is ethylene diamine, which is and there are like ammonia gives one pair of electron, which is a monodentate, but ethylene diamine gives two pair of electrons, those is called bidentate. So similarly, EDTA and all that right? Yeah, EDTA, ethylene diamine. Yeah. This is what is an acid, ethylene diamine tetra acetic acid, right? So that means this nitrogen as a lone pair, So similarly on the minus, once you remove, so it will become minus. Sometimes depending on the pH you can remove all the 4 hydrogens, or sometimes you can remove only 2 hydrogens from 2 groups. So it can be, but it normally, what is the denticity of this? Excidentate ligand. So this is one of the strongest ligand that is known, because it all the 6 groups binds very strongly, and in agriculture this is EDTA, zinc EDTA complex, iron EDTA complex are used by the farmer. These are all supplements given to the, like the way that we take supplements. If you want to give the supplements to the plants, if you give zinc powder, if you go, or zinc salt, if you go and put it to the plant, it will be, they take too much and it will become difficult for them to survive. But if you give this kind of a complex, only when it is necessary, there are enzymes which will break and then allow the zinc to get assimilated with the plants. Too much metal ion to our body also is very toxic. Similarly, toxic to plants also. But if you give them in the form of this complex, only when it is necessary they will assimilate. So they leach out the zinc or iron, other things, other metals by the bacteria. Bacteria will chew this and then make the metals available. So there will not be excess of metal ion and will not be toxic. Like I told you, it will be toxic to us if you take too much of any metal ion content, except probably if you are anemic, ferroammonium sulfate is what is actually given doctor, but you will not know it. The tablet is actually ferroammonium sulfate. I am not saying in the laboratory you take ferroammonium sulfate and use it as a supplement. Never do that. Okay. So I'm just giving you example that how these elements are used. So excess. In fact, if you take iron supplement, your body gets heated up because it is working too much to allow the iron to get assimilated. So these are all the different kinds of ligands that are used to hold the metal. So free metal ion cannot be present by itself. So it is always associated with some of these groups, which are what are called ligands. They can be water, they can be halide, or ammonia, or different kinds of ligand. There are so many halides. You have only chloride that I have put. You have fluoride, bromide, iodide, all that is there in addition to chloride, halides. So the way that the carbon containing, nitrogen containing, oxygen containing, and then halides. These are the 4 different kinds of ligands. Carbon containing ligands. Carbon monoxide, cyanide, correct. So carbon containing is carbon monoxide and cyanide. Okay. Okay, nitrogen containing is ammonia or ethylene diamine, EDTA, not EDTA, phenanthrene, bipyridine, any different kinds of ligands. They can be bidentate, can be monodentate, can be multidentate, right? So multidentate generally is hexadentate. EDTA is one of the most common ligand that is known to bind most of the metals. One of the strongest ligands. So then oxygen is water, ethanol, methanol, all kinds of molecules containing oxygen. And then halides, I already told you, fluoride, chloride, bromide, iodide, right? And this is how the strength of these ligands. That means the ability to bind metal. That strength depends on the ligand, what type of ligand. So carbon binds much more strongly. Cyanide, complexes are very, very stable. They bind metal very strongly. So this is the order of that, binding capacity, or which make them very strong complexes. So carbon, nitrogen, oxygen, and then halide. So carbon carbon monoxide comes under the organometallic chemistry, which is a non-classical coordination chemistry, and cyanide comes under the classical coordination chemistry, right? So when you when you have studied, or when somebody is going to give you lecture on organometallic chemistry, you will often see carbon monoxide. So but in the classical coordination chemistry, you don't come across carbon monoxide. So but that is how you classify these ligands in terms of their strength to hold the metal very strongly. So carbon monoxide and cyanide, many different kinds of cyanide complexes are known for all these transition metals, FeCN6, 3 minus or 4 minus, ferricyanide, ferrocyanide, you must have come across, right, some of these compounds. So similarly for other metals also, these cyanide complexes are known. So they bind very strongly, and you can see that is the order that I put there. Cyanide is the first, and then followed by ammonia, and then you have oxygen and nitrogen. So these are all, this classification is coming from all this crystal field theory that we already know. Otherwise people did not know before where to put what. And we will talk about that, what is this crystal field theory, how people, have you studied anything about crystal field theory? All of you? Okay. Is there in +2, I know. But still in MSc, people don't remember many things. Some of the details, very important details are, students don't know. Okay. So now, I coming back to the question that I have put here 4 and I have put here, the 3 or 6 water I have put, but I have put only 4 chlorides, and similarly here also. This is something in between also I can put, but these are the most common compounds containing either 6 water or 4 chloride, or other halides can be there, right? So how do you explain this? So the most common compounds that are known for coordination in transition metals, those containing 6 ligands around the metal, they are the most common. Okay, those are called octahedral complexes, right? I did not bring the model to show you why it is called octahedral in spite of it is having 6 ligands. 6 ligands, why octahedron? So that it depends on the shape of the molecule. So if you look at the octahedron, it has 8 faces. So that's why it is called octahedron. So let us look at into the why they have this many ligands. I have only given most the common is for cobalt, nickel, copper is all very common. Similarly, if I want to write for see, for example, copper sulfate pentahydrate, or copper chloride 2 minus. Okay, and the kind of geometries that copper show, or manganese show, or iron compounds show, are slightly, there are differences. And how do you explain the differences of these geometries of these molecules? So that is where the crystal field theory comes into picture. So that means CFT, it stands for crystal field theory, right? So there is some kind of a force that is available for these ligands to get coordinated. And first time they have observed all this, these material, people used to study materials in the solid state long ago, and they observed all this in the solid state, and particularly crystalline materials. And since they observed first in those crystalline materials, this force is there in water also. But first time when they observed in crystals, they thought it is only there in crystals, hence they called it crystal field theory. So there is a field, there is a force, but it is there in the solution also. Later people came to know. Since the first time when they observed, there seems to be some force operating to make these metals have only 5 ligands, 6 ligands, or 3 ligands, or 2 ligands. They observed, So that's why that field refers to your force, and first observed in the crystals, hence it is called crystal field theory to explain the structure, bonding, and properties of these compounds. So structure means that we want to know what is the shape of these molecules. Bonding means we want to understand how these ligands and metal interact with each other to give only a particular geometry, octahedral geometry, tetrahedral geometry, a square planar geometry. That is the structure, right? And properties. Are they colored? Are they magnetically active? And what are the applications that they can provide? There are a lot of applications for these transition metal compounds. In industry, for example, if you want to synthesize sulfuric acid, nitric acid, without these metals is very, it will be expensive, very easy to make using the metals, so they are the catalyst. So that means that is where the applications are, right? So let us look at some of the structures of these molecules. So when I write MnCl2 6 water, is actually what it means is Mn is bonded to 6 water. So this is then you have manganese is the +2 oxygen state, and then you have chloride, 2 chlorides outside. Charge balance Mn2 plus 2Cl minus. So they have to be neutral molecules. So these 6 ligands are bonded around the metal, right? So but if there is a chloride, there are only 4 of them that are present. Okay. So when you say this kind of the geometry, that means when 6 ligands are around the metal, they are not planar, right? You can imagine a plane where for 2 year, 2 year, 1 year, and 1 year, so they are not planar. So it is called octahedral geometry. I should have brought the model, I did not realize that. Octahedral geometry. Is again it looks like a benzene ring, not. So it is an octahedron where 8 faces are there and 8 vertices are there. Vertices, 8 vertices are there. So each vertex has one ligand. I'm sure probably you would have seen the model of what is an octahedral model look like. If you look at that, then you will know that in spite of having 6 ligands, it is called octahedron because it has 8 faces. So each vertex has one ligand. Now what is the geometry of this is an octahedron I have already written, but in octahedral geometries there are perfect octahedron, there is a distorted octahedron, right. So what it means is, distorted means, when I say perfect octahedron, that means the ligand to metal distances are the same. That is what is a perfect octahedron. But if ligand to metal, one ligand to another ligand, there is a difference. Let us say the 4 in the center are of one kind, and 2 here, one above, one below, are of a different kind. Then you call it a distorted octahedron. They can be, this 4 can be longer and the shorter, or the 2 can be longer, right? Or vice versa. 2 can be shorter and 4 can be longer, or 4 can be shorter, 2 can be longer, right? So that is what is called distorted octahedron. Octahedron or octahedral geometry. So how do we know, and how do you arrive at this? Some of these metal complexes have all these kinds of geometry: tetrahedral, octahedral. I told you most of the metal complexes have octahedral geometry. The most common geometry for transition metal complexes is octahedral, right? And the next most common geometry for transition metals is tetrahedral. Okay. So we want to understand why this some of them, why it is most common octahedral, why the next common is tetrahedral, is we want to know, right? So we are using crystal field theory to understand structure, bonding, and properties. Under properties, we want to understand whether they are colored or paramagnetic or diamagnetic. And applications. So this crystal field theory particularly explains structure, bonding, and properties. Okay. So let us look at the structure. I have already given you, majority of them are octahedral, and next majority is tetrahedral, and among the octahedral, some of them form a perfect octahedron, some of them distorted octahedron. So we want to know why this happens. So according to crystal field theory, you need to recall the d block elements have 5 d orbitals. S has S, there is only one, P3, right? Px, Py, and Pz, and then D has D, dxy, dyz, dxz, and dz square. So these are all very important to understand, because they are the one in the case of d block elements. When we say d block elements, that means valence electrons are present in the d orbitals. And when you say pr, this all these contain valence electrons are in the p orbital. So they're called p block elements, right? So S belongs to that alkali and alkaline earth metals, because valence electrons are there in the s orbital, right? So now we are talking about d block elements. So that means we need to consider the shapes of these orbitals. So if you look at the shapes of these orbitals, so you need to so in the coordination axis, you can put these 5 different orbitals in you can categorize them into 2 different kinds, particularly x square and minus y square and z square. For example, z square will sit on the z axis. Okay. So, x square minus y square will sit on the x and y axis, whereas the other three will sit in between the axes. So, they do not, these two, like what I have represented, z square sits only on one axis. So, similarly, x square minus y square sits on the axis. So, it sits on y square and y and x. So, it sits exactly on the axis, whereas the other ones, they sit in between the axis. So, when I say x y which will sit in between the axis, that means they do not sit directly in the axis. So, those sit directly in the axis are these two, and those sit in between the axis are these three. So, one of the theories, whatever this crystal field theory, what it says is metal and ligand, they ligands approach the metal. So, you consider metal as a charge, ligands also charged. So, charge repulsion, or it can be attraction can be there. So, here basically they talk about repulsion. So, because these two orbitals are sitting directly and they approach through the axis only, according to the coordination axis only, randomly they do not come. They have to approach through these axes. Okay. So, when the ligand approaches, let us say ligand is approaching along the z axis, particularly if it is a dz square, because it is sitting on the axis, not in between the axis. In between the axis is this. See, x and z. This is in between the axis, right? Z square has only one lobe, but the x and y has 4 lobes. But they are in between the axis. What is the in between axis? X and y, you see here, this orbital is in between the axis. But when the ligands approach, they approach only along the axis. Okay. So, when they approach along the axis, because these two orbitals are lying exactly in the axis, there is more repulsion. Okay. So, that so these 5 orbitals have the same energy in the absence of a ligand. When there is no ligand, these 5 orbitals have the same energy, but once the ligand approaches, they get separated into 2 different kind. Okay. So, this one is called T2G and this is called EG. So, T refers to triply degenerate. So, T refers to triply degenerate. E refers to doubly degenerate, and G refers to what is called Girard. That means it's a German word. Let us say, forget that there is a green behind. Assume that both side green or both side this. So, if I invert it, I will get the same picture. Okay. So, in an octahedron structure, if I invert, I get the same picture. So, there is no change in the geometry. That is what it means. So, such molecules will have G. Octahedral molecules have that. If I had brought that octahedron geometry model, that if I had inverted, there will not be any change in the structure. So, that means such molecules will have that the letter G. That means there is no change in the geometry even if you invert it. That is what it means. Inversion center of symmetry, they have inversion center of symmetry, but on doing that, there is no change in the geometry, and such molecules containing that kind of a symmetry will have G. Okay. And since there are 2 of them, and E refers to doubly degenerate, E is doubly degenerate, T refers to triply degenerate. But now if you look at this, I have put 2 here. I did not put TG or T1 I did not put. So, why that 2 is there? No clue. It will not be there in the textbook. Normally people don't explain all this. But if you know the subject, it is very easy to find out. So, here you have 3 of them, p orbitals, which are also triply degenerate. And this set is what is called T1G. One is already used there. So, second set is T2. Okay. So, here these, so this is T1, that is T2. Because here also these 3 are triply degenerate, but not of the same kind like P, they are of a different kind, and hence that letter 2 is used, T2. Okay. So dx, whatever I have put here, xy, dx, dyz, dxz, and here dx square minus y square, dz square. Okay. So that means the energy difference between these negative 0.6, negative 0.4 and negative 0.6. So that means here it is smaller and here it is. So let us say I have a complex containing 10 electrons. Okay. So this is the only way you can arrange, because these 3 one by one you arrange 1, 2, 3, 4, 5, then 6, 7, 8, 9, 10, right. So if there is a D10 system, this level and that level is equally occupied, there is no role of a crystal field. So there is no role of a crystal field because both the levels are equally occupied. The crystal field theory, so D10 zinc 2 complexes don't have any crystal field energy. So anything in between comes into picture. Okay. So if I remove an electron here, correspond to what compound? Very good. Copper 2. Copper 2 plus zinc 2 plus is D10. Copper 2 plus is 3D10, 3D9, right. So this one, if you look at this, now the question is, this electron I have put it here, why should it sit there? Both the orbitals are of the same energy. This orbital and this orbital same energy, right? Why should the unpaired electron sit here? It can sit here. I will put the pair here and take the unpaired there. Can be done, right? Done or not? Huh? Huh? No? See, let us say, there are 2 positions which are of the same, and you want to go and she also wants to go, isn't it? So same way, it makes a difference to put where to put that unpaired electron, whether to put it here or put it here. I have put it here because I removed one electron. I can remove an electron from here and then pair this. Not possible? It is possible. Because it is possible, it leads to what is called distortion. Okay. So this is what is called uncertainty principle. What is uncertainty? Electron 1 is sitting here and then it is sitting here, keep changing because they have same energy. Okay. And this leads to what is called distortion in the energy level. So that uncertainty, not the uncertainty principle of quantum. Okay. Uncertainty here, where to sit. You are not certain, right? Whether to go here, to go there. You are not certain. That is what is uncertainty. It is an English word, not a principle. Uncertainty principle is in quantum chemistry, right? So because of that, there is a change in the, the energy levels get changed. Now these 2 levels, so let us say, here d z square dx square minus y square. So similarly, here I change Now, equally filled, whatever I have changed, and I will tell you why I have done this way. Okay. So now there is a change in the energy level, because to prevent that kind of an uncertainty where to sit electron, this is what happens, and this what gives rise to what is called Yan-Taylor distortion. So copper 2 complexes are always known to have distortion in the geometry. What is the distortion? That here I told you in the case of manganese 2 plus that all the 6 ligands around the metals are equidistant. That means there is no distortion. It is a perfect octahedron. But if you take copper, aqua complex 2 plus, so it will have so that means the 4 in the center of one kind and 2, one above, one below is of a different kind. So that means it is because of this distortion. If electron, let us say this one will not have any problem. Okay, 2 electrons, because each orbital has one electron, there is no problem, right? Only when there is unequally occupied, that is what is whenever it is unequally occupied, unsymmetrically filled, that distortion happens. But once you have this, no problem, it will be a perfect octahedron. So whenever this unequally filled, particularly copper 2, because to eliminate that uncertainty where to put, now I have changed. So there is a variation in the energy levels. There is a difference in the energy levels, and there is no such thing as one electron is there, it has its own orbiter. Here 2 electrons, it has both of them are filled, right? So similarly these are filled. Now if you ask me why I put it this way, why not take this one there, or why you put these 2 orbitals below? So if you look at it, those orbitals containing Z component I have put below. So dz square between these 2 is lower in energy. Now in this, among the 3, those containing xz and yz I put. So Z component containing orbitals are below. Okay. So the reason is, now if you look at this, according to the coordination x, y and z here, z is here. So that means water is along the z. So that means it's too far away from metal. So less repulsion. So that means more stabilized. More stabilized means go in energy, lower in energy. Okay, understood or not? So because the Z component is away from the ligand metal, Z ligand, the water ligand along the Z axis away from the metal, so there is less repulsion. So crystal field theory talks about only repulsion between the metal and the ligand. So that metal is charged, ligand is charged, so both repel each other. That is what is crystal field theory is about. Okay. So now less repulsion along the Z axis, because I put the Z axis here, correct? So along the Z axis, 2 waters are far away, or indirectly this is the configuration it will have, giving you this kind of a. So this is what is called what kind of distortion? Z out, right? So Z out, you can see here is out, out from the original place. So that's why this is called Z out. So majority of the compounds fall into this category. Okay. So this is this kind of a distortion was identified by these 2 guys together. So it's called Yan-Taylor distortion. Some call it John, but some call it Yan. J is silent. So we call it Yan-Taylor distortion. Those who are not familiar, they call it John-Taylor distortion. Okay. So, this is what is the distortion arises because of the occupying the electron occupying the orbital which have the same energy. Uncertainty arises because the unpaired electron or a paired electron, why should it sit? The paired electron can sit here, unpaired electron can sit here. So, that means to remove that kind of an uncertainty, that there is a separation in the energy that takes place. Now, there is no longer such an uncertainty, and these guys identified. Isn't that wonderful that how many have thought about that? But these people have thought about that. Now we have understood how this works. But these are all coming from the, again, this is part of the crystal field theory. Okay. Originally crystal field theory was proposed, but later on some of these things to understand how, using the crystal field theory, how you can explain. So it is clearly explained now. Now, which is the system containing, now we have 2, 4, 6 plus 8. So D8 system, what is an example for a D8 system? 3D8? Nickel 2 plus. Nickel 2 plus never undergoes any distortion, gives a perfect octahedron. So how nicely people have explained, isn't it? Nobody thought about, did any one of us think about that? No, I don't think it comes to us, or did not come to many, but these two people have identified. Now we understand how it works, and it is generally applicable to all the systems. You can explain now whatever this Taylor distortion that we talk about, you can explain any of the systems. So if you, now manganese 2 plus, what is the configuration for Mn2 plus? What is the D configuration? Huh? No, Mn2 plus. Yeah, 3D5. Right? So now, three here, 2 there. So the lower level 3 equally occupied, upper level 2 equally occupied, no problem. So hence it forms a perfect octahedron, right? So this is how is explained. Manganese 2 plus in fact is is perfect octahedron. Copper 2 plus, any compounds that you take, they always will have a depending on the ligand, it always undergoes a distortion. Depending on the ligand, the distortion can be very severe or it can be small. Okay. Sometimes if you want to measure these, when you measure the structure of these molecules at room temperature, and if you measure the structure of these molecules at lower temperature, let us say liquid nitrogen, you can cool them to liquid nitrogen and measure the, collect the data and look at the structure. There are differences people have found that at low temperature, at room temperature, some of them, if you have a chelating ligand, what happens? There is a dynamic distortion. That means presses and then elongates, presses and elongates. What presses? Let us say I have an ethylene diamine. So ethylene diamine, it has only 2 carbons, so which is very short. So what it will do? Ethylene diamine, it will press the nitrogen will be closer to metal. And if you take this diamine, now it is not that short, so it will not press the, it will not, so that is what is it will not press the nitrogen very close to copper. So it will not, you will still see the distortion, but in case where ethylene diamine is there, you don't see distortion because it is pressing it. So which is called dynamic Taylor distortion that happens at room temperature, because at room temperature you have energy for it to go on and off. But when you freeze it, then this on and off gets freeze, it gets frozen, and hence you will be able to see the distortion. But at room temperature people found, hey, there is no distortion. It is because of the energy, that is room temperature energy is so high that rapidly this on and off is going on, X-ray is not able to determine the distance. Okay. So such kind of distortions are called dynamic Taylor distortion. So now I have told you that why this kind of a, now I have put here some values. Okay. So if I put all the 6 electrons, that each orbital can take 6 electrons, each orbital can take 2 electrons, there are 3 orbitals, so it can take totally 6 electrons. So, upper one take total 4 electrons. So, if you calculate, so assume that, can you tell me an example where D6, what is an example for complex containing 3D6 configuration? Fe? Fe2 plus, okay. Anything else? Cobalt? Very good. Cobalt 3 plus. Yeah. There is a difference in this charge. So, once it is plus 2, the field that it can exert will be different from plus 3. Okay. So, plus 3, the size matters here. So, plus 2 will be bigger compared to plus 3, isn't it? Plus 3 will make it very small. So, when it is small, ligand comes very close, so repulsion will be more. Correct or not? When it is small, ligand will come very close, so repulsion will be more. And in the case of cobalt 3 plus, for example, this energy separation between the T2G and EG increases. So, what it happens? So, I have 6 electron, I would put 3 here and 2 here and 6th one here, but it will not, because the energy separation between this level and this level is so high that all 6 will sit here. Understood or not? So, that means repulsion is more. So, that means this total, this whatever I am calling overall delta O, that energy separation will be more in the case where charge is more, because they approach very close to the metal. So, there is repulsion is more, and hence the crystal field energy is more. Okay. So, because of that, if the separation between this level and this level is close, so now first electron will go to the lower level and then go to the upper level. If it is large, they sit only in the lower level, and that is what happens in the case of cobalt 3 plus. But in the case of iron 2 plus, it will not happen. If you take same ligand, ammonia is, for example, is same ligand. So, that means it is nature of the ligand, nature of the metal, charge on the metal, so many things changes, so many things here, right. So, that is how the crystal field theory is basically repulsion, and this repulsion, how they happen, how it changes the energy levels, and that's how it changes the geometry of the complexes. And once the geometry changes, the properties also changes, and once this energy level between the upper level and the lower level changes, number of electrons that can be there in the lower and upper level, number of unpaired electrons also changes. So, in the case of D6, if the level, 2 levels are close to each other, then I will have 4 unpaired electrons. But if energy level between the 2 is too far apart, then I will have 0 unpaired electrons. You see how it is paramagnetic and diamagnetic, and find out. Did you understand what I am saying? Huh? Understood? Now you have been thinking, so I will explain. So, distortion I have explained. Now I will go back and show you how the so we are talking about 3d6, which is cobalt 3, that means there are 6 electrons, right. So, 6 electrons according to Wundt's rule, that assuming that there is the separation between these two is not much, they are very close to each other. So, that means 3 electrons and 2 electrons will go, and the next one will come and pair here. So, that means this energy, this whatever delta O, the total energy here, whatever I put here, 1 compared to this one, this delta O2. So, delta O2 is much greater than delta O1. So, in this case what happens, all the they will occupy first all the 3 orbitals, then followed by this. So, this makes it diamagnetic, this makes it paramagnetic, right. So this is paramagnetic by 4 electrons, this is diamagnetic by no electrons, 0 electrons, right? And that's how in the case of cobalt 3 plus becomes diamagnetic. So cobalt 3 plus is diamagnetic, and now imagine what is the, the numbers that I wrote earlier, I will put that back. So 0.6 delta O and 0.4 delta O, and that's how in a total together, if you multiply 6 electrons by 4, 2.4, here 0.6 for total 4 electrons, if you multiply it will be 2.4. So plus 2.4 minus 2.4 will get cancelled out if it is equally occupied. So which is the case in the case of manganese 2 plus, which has a d5 electrons, and water is a weak filled ligand, and manganese 2 plus also charge is less compared to manganese 3 or manganese 7 if you compare. More charge, smaller the size. Smaller the size, closer the ligand it comes. Closer the ligand it comes, more repulsion. That means this separation between these two levels will be large. Okay. So that leads to now diamagnetic or paramagnetic. How many unpaired electrons are there? Paired or not paired? Many things can be determined. So in the case of cobalt, compared to cobalt 2 plus, so I will write down the complex. So if you look at this, this is paramagnetic and this is diamagnetic. Okay. So because in the cobalt 3, because plus 3 charge is there, smaller the size, more repulsion, more energy separation between the two levels, and the electrons will not be able to go up here because there is so much of energy. They have to overcome that energy. So pairing takes place, right? But in the case of cobalt 2 plus, so it makes a big difference in the charge, plus 2 and plus 3. So in the plus 2 case, this will be the scenario, and plus 3 case, this is the scenario. So it makes it paramagnetic. Now in the plus 2, you have here 3d7 and here you have 3d6, right? Now you fill the electrons here, 7 electrons, and you will find out that there will be 3 unpaired electrons in the case of cobalt 2 plus. So it's paramagnetic by 2 unpaired electrons, and in the case of cobalt 3 it is diamagnetic, no unpaired electron, right? And the crystal field stabilization energy can be calculated. Crystal field stabilization energy is determined by how many electrons are there here multiplied by that negative 0.4 delta O plus the number of electrons, let us say N1 plus N2 0.6 delta O. Okay. Now if you do that for this system cobalt 3 plus, there is nothing here. So negative 2.4 delta O. Okay. So and that is the maximum stabilization possible. So crystal field stabilization that a metal complex can achieve is maximum 2.4, because if you put 1 electron, then it gets subtracted. 1 electron up if I put, then it gets subtracted because plus 0.6 is there. So anything that goes above will subtract the electron, making it less stable. So this is CFSE refers to crystal field stabilization energy. So that means the complex will be very stable. In fact, cobalt 3 complexes are much more stable. What is the stability that I am talking about is, there is a kinetic stability and then there is a thermodynamic stability. Two different kinds of things are there. What is kinetic stability? I put this complex in water, it will not get exchanged with water. Okay. So let us say I add water. You take copper ammonia complex, add water, you get copper water complex. it can be 6 here, but I always will have 6 ligands. 4 is very easy to make, but if I add excess ammonia, it will form 6 complex. Okay, so very easily I can make water complex. Take ammonia, copper ammonia complex, you add water, keep diluting, it will become light blue. This is very dark blue, it becomes light blue, indicating that water is getting exchanged. But if you want to do the same thing, it will not happen. Even if you add HCl and heat it, you will not be able to replace ammonia. So that means this is what is called kinetic stability. Thermodynamically both are stable. What is kinetic? That means exchange of ligand. Is a reaction. Kinetic means what? Is a reaction that we are talking about, right? So there is no such thing happening in the case of ammonia. It is because it has achieved maximum stability that is possible. So this is what is called crystal field stabilization energy. And if you look at Werner, he has used ammonia and cobalt 3 complexes to study all this. He did not know crystal field theory before. This is what is called intuition. These are all genius people. He did not know anything about theory, but somehow he used and he found out all things he would, if you go back and read the book, 5 ammonia 1 chloride, 4 ammonia 2 chloride, 3 ammonia 3 chloride. He was able to make all of them because of the stabilization energy. If they are exchanging like in the case of ammonia, you cannot do that. You cannot be able to find out isomerism, whether a trans or a cis, whether ammonia is there or chloride is there, what is there, you will not be able to find out. But in the case of cobalt 3, because it achieves some maximum stabilization energy of negative 2.4 delta, this is what is possible maximum, and that is true for cobalt, and that's why he has used all different kinds of chloride and all that, and he has shown isomerism. 1 chloride and this has only 1 chloride. He is able to isolate and show through different spectroscopy. And if you put here 5 ammonia 1 chloride, this energy separation will be different. And if I put 2 chloride, the energy separation comes down because chloride is a weaker ligand compared to ammonia. I did not write in that series, I put only halide. So fluoride, chloride, bromide and iodide. So fluoride is the strongest field ligand. So he used the most common ligand chloride, because sodium chloride commonly available. So chloride anion is very common in the nature. That is what something is used. So this is what is called intuition, and the only genius people will know that. So he did not know anything about the crystal field theory. Crystal field theory came only after 40, 50 years only theory came. Before that itself, he has done all this. But he did not know, but somehow intuition has given him that I have to use cobalt 3 complexes. These give very stable complexes. If you go back and read textbooks, you will find ammonia 3 ammonia or 4 ammonia 2 chlorides, 3 ammonia 3 chloride or 2 ammonia 4 chloride. All this possible depending on the concentration and the condition. If you apply, all this is possible because of the stability that you can achieve with the but in the case of copper 2, if you calculate, stability will be very, very small, because 3 electrons are sitting here, they will subtract the stabilization energy. So anything that is there upper level will subtract the stabilization energy, anything that is sitting here will stabilize. So for cobalt 3, that you can achieve such a stable configuration, and hence it is possible to study and show that where is the how many chlorides are there, how many ammonia is there. It's very easy to do reaction. If you put to ammonia, you just add HCl, immediately ammonium chloride will form. But in this case, it doesn't. I told you, if I add HCl to this, ammonium chloride will not form, because ammonia is bound to cobalts very strongly through the stabilization energy. So it's very difficult to, in fact, some of these experiments are done in the laboratory, and if you know this chemistry, you will really enjoy and you understand why this is happening. People will digest for several hours to convert the ammonia to chloride complex or water complex, because once H plus and ammonia react, it will form an ammonium chloride. So water will be there. So water complex, for example, if you want to make, or if you want to make a chloride complex, is the only way to do it. So you can see now how this crystal field theory and other people associated, Ann Taylor distortion, I said, depending on where the electron is sitting and how the electron is sitting, depending on the charge on the metal, depending on what is the kind of ligand. So many things are important to understand many of these things. Now, whether this the difference between this level and this level will also tell you what kind of energy that it will absorb, right? So this will be in the probably in the visible region, let us say. This will, once it is there, you need a much lower wavelength, that means higher energy. So that means it will probably go to the UV region, and that's how whether they absorb in the, even in the visible region there is a small differences depending on whether you have a chloride ligand, how many chloride ligands, because I already told you, carbon, nitrogen, oxygen, and then halide. So among the halide, fluoride, chloride, bromide, and then iodide. Okay, so that is the order. And since chloride is more common in the nature, so it's obviously that is the ligand people have used. So that's how you will find out. And since chloride is a weaker ligand, if I replace ammonia, if I remove all ammonia and put chloride, immediately it will go to tetrahedral geometry. That's again another just the reverse of this happens. Because of the weak field ligand, if it is there, they prefer to have tetrahedral geometry. So most of the complexes are formed by the weak field ligands that having halides. Everywhere I wrote CuCl4 2 minus, MnCl4 2 minus is what I wrote. So chloride. So that means these halide, other ligands are also weak. So that means once you have this weaker field ligands, they prefer to form tetrahedral geometry. But other ligands prefer octahedral geometry because they achieve this stabilization energy. And when you compare the tetrahedral, which is little opposite of this octahedral, the energy is very small, and hence they don't prefer to, when you don't achieve an extra energy, why form that complex? Only when you achieve an extra complex, extra energy, only that complex will be formed, and that is the reason why octahedral complexes are more common, because they have more energy compared to tetrahedral. Tetrahedral will have much less energy compared to 50% less, about 45% less compared to octahedral. So when you can achieve more energy, hence they prefer to have octahedral geometry. Okay. So many of these things, the color also, how it changes, the variation in the energy. If they come closer, they will be in the probably infrared region. If too close, infrared region. Too far away, they will be in the UV region. That is determined by the strength of the ligand. So cyanide is one of the strongest ligands. So that will make it very large separation between this level and the upper level. T2G and the EG, this is applicable to octahedral complexes. And tetrahedral complexes, that G is removed, and there will be an inversion of these energy levels. All these 3 will go above and 2 will come below, and that G is removed because tetrahedral model, if you look at it, there is no inversion center. If you invert the tetrahedral geometry, it will not give the same configuration. So hence that G refers to there is an inversion center. So in tetrahedral there is no inversion center, that's why that G is removed. So same concepts can be applied, and then you can understand, and the energy that it can achieve compared to octahedral is smaller, hence the number of complexes that form tetrahedral geometry are less compared to octahedral. And why these differences between the among the octahedral complexes, one is diamagnetic, other one is paramagnetic, one is very stable, one is less stable, and all that is depending on what ligand is present and how much separation is there between the 2 levels. So this is what is crystal field theory is all about. Okay, so that is probably is 4 o'clock. Maybe I'll try to see if I can whatever is missing, maybe I'll do it in the next class on a Monday. So you all read all this and come. There will be, I'll give you some question paper, maybe 10-15 minutes you have to write, and then I will find out how much you have understood. Okay, so I'll stop here. Okay, maybe one of the students can help me to erase this board. If you have any questions, I will be able to answer. See if you
Why not it is possible
Possible. But more common is Z out. Okay. You need a special ligand for Z in. You need a oxo ligand, for example, which forms a very short metal oxygen distances. They will give you Z in. Such kind of complexes are difficult to make. That's why it's not very common. Very rare. If you don't ask questions, what it means is you have understood everything or you have not understood anything. Two things. So, understood everything. I'll tell me, when I give you a question paper and see your answers. No questions? Others in the bank very silent, not talking. Okay, otherwise, thank you. Hope you have, learned something that you had read before, but you were not sure. Now, probably that clarified, I am assuming. Okay. Yeah, if you read textbook, you will not get all the information what I am giving you, or you will not be able to understand. That is an advantage of teaching for a long time in places like IIT. Because students challenge. If I go to BTech class and tell this, he will make fun of me if I say anything wrong. So that means I have to be sure. Okay, they will clap. Of 80 students, if there is anything wrong, they will clap. Right can be clap, wrong can also be clap. Okay, thank you.
SwayamPrabha, Digital India, Educated India.